Welcome to CS 320, Chapter 2, Variations on the Turing Machine. And in this case, we're trying to design a Turing machine that could be more powerful than the Turing machine that we've learned about already. So a couple of ideas are the move in the state. So instead of having the move on the edge, we'd have a move inside of the state instead. A stay option is so that we don't have to move the tape head. A two-way infinite tape is having an infinite number of blanks, both forward and backward. And then the kTrack Turing machine means that we have more than one tape head to work with. And a non-deterministic Turing machine means that instead of only having one path to follow for per letter, that we can actually have two paths and make a non-deterministic Turing machine. All of our Turing machines so far have been deterministic. Now you can read about most of these in the book. I'm not going to really cover them, but basically they say that even if we did this, we can get a regular Turing machine to simulate them. And that's also true for the two that we are going to talk about, the kTrack Turing machine and a non-deterministic Turing machine. Adding non-determinism will not increase the power of our Turing machine. We can create a Turing machine that will simulate a non-deterministic Turing machine, and so a non-deterministic Turing machine isn't any more powerful. The same with a kTrack Turing machine. So the way the book talks about a kTrack Turing machine is you can really think of this as a one-track Turing machine. And then our character, the input characters that we put on our machine, instead of just being one character long, could be three characters tall. So you can have AAA or ABA or whatever you want to be on each one of these. We could basically just combine this into one tape that has three characters on it. So we have lots and more characters, but we can pretty much simulate that with a regular Turing machine. Another way that I thought, and this isn't in the book, that I thought that we could simulate a kTrack Turing machine is just put some sort of marker here in between that is a marker between the different tracks or tapes that we have on our Turing machine. So this tape would fit in here, this tape would fit in here, this tape would fit in here. Now, what would we do about the infinite number of blanks? Well, whenever we run into one of these markers, we could just insert a blank, which will move everything down, so we can always insert a blank. The other thing that we need to worry about is what about the tape heads? Now, the Turing machine that the book talks about says the tape head is always pointing to the same character, the same cell on each track. But I think we can even have the tape heads point to different locations on the track, and that could kind of increase the power of that. So how do we know where the tape head is? And that is, we have our input or our characters that we put on the tape. And so maybe we have an A and a B and a C and so on, or whatever our input characters are. They can have the hashtags. And then we can have a different color of input characters, A, B, C. And we mark where the tape head is by using the red colored characters. So if we have this on our tape head, then we know that the tape head for the first tape is pointed at B. So we can always go through and wait until we find the one character that is not the right color, and we know that's where our tape head is. So then we can move down over here, move the tape head of this machine down here, and we can simulate the tape head of the kTrack Turing machine. So you can read more in your book on how you would simulate the kTrack Turing machine with a regular Turing machine. But now let's move on and talk about non-deterministic Turing machines. All right, now we have a non-deterministic Turing machine, and it's not really important what this accepts, but you could see that there are two paths to choose if we're reading an A on our tape. And notice they write something different to our tape. So now with non-determinism, with finite automata, it's just like a matter of being in two different states at the same time. But now we could be in two different states, and our tape can have two different things on it based on which path we choose. So it's going to be a little bit harder to simulate a non-deterministic Turing machine with a deterministic Turing machine. So how are we going to do it? Well, step one is we're going to label each edge or number each edge inside of our Turing machine right here. All right, so you can see that if we read a B, write an X and move right, that's considered edge one. If we read an A, write an X and move right, that's edge two. If we're reading an A and want to write a Y onto our tape and move right, that's considered edge three, and so on. So now that we've done that, let's go ahead and use a deterministic Turing machine. I'm going to use a 3-tape Turing machine, or so that we have 3 tape heads, and that just makes it a little bit easier. Of course, a 3-tape Turing machine can be simulated by a 1-tape Turing machine, but we're going to, just to explain it, we're going to use this 3-tape Turing machine. Okay, so on the first tape is going to be the working tape. This is where we can do the operations as we run the word. Now, sometimes the operations we do, we might choose the wrong path, so we might want to rewind and start over. So that we can do that, we'll make sure that we have the original input word on the tape. Now, as you can see, I've just inserted a blank onto the beginning, and that's just so that we have a marker so we don't fall off the left edge of the tape and accidentally crash. In fact, this deterministic machine will never ever crash. The non-deterministic one might crash, but our deterministic one will never crash. There's only 2 things that it will do. It'll either halt or go on in an infinite loop. Because what it's going to do is it's going to try to search for all the different paths that we could possibly take and see if there happens to be one path that goes from the start state to the halt state. And how we're going to do that is we're going to ask for mom's advice. So this is just to explain it. I'm going to elaborate more on how we actually generate mom's advice. But mom might come up with a set of numbers. And those set of numbers are the different paths we should take into this machine. So mom might say, well, we should take path number 5, 7, 8. Okay, so if we look at this and we're in our start state, right off the beginning, we're like, oh, path 5, we can't take path 5. That doesn't work. So we can't do that. So what we would do is we'd erase our working tape, copy the original word back on here, and then ask mom for a new set of advice. So Mont goes ahead and generates a seemingly random set of numbers that tells us, okay, try taking these paths. Now 3, oh yes, we can do that. So we'd actually see, okay, I take the A, I write a Y and move right. So I'd actually go ahead and perform that operation by taking that A off, putting it to the right and moving the tape head over here. And then we see take path 4. Well, path 4, yes, I could take that path, but my tape head is pointing at an A, and path 4 says that I should read a B instead. I can't take that path. And then we're like, oh, mom, you gave us bad advice. So we go ahead and we rewind, erase the working tape, copy the original back onto the working tape, and ask mom for a new set of advice. Now, we keep asking mom for new and new advice until mom happens to come up with a path that not only leads us from the start state to the halt state, right? But also, as we're doing it, we're actually reading the letters that are on the input tape, and it doesn't lead us to crash the tape by moving left. So in other words, we're just going to keep asking mom for advice until we get lucky enough that it happens to be a path from the start state to the halt state, and all of these moves make sense. And when a mom finally comes up with that advice, then we'll halt. Now, eventually, we might search all these paths, but we have to keep searching because there are loops in our machine. So there's an infinite number of paths that we can take. That's okay. Our machine will just keep regenerating advice again and again and again until it happens to find a path that works. What if it never finds a path that works? Well, then it's just going to go in an infinite loop. Remember, Turing machines can either accept the word by halting, reject the word by crashing, which we'll never do in this case, or reject the word by going into an infinite loop. Now, it's not so helpful for us because we don't know if a word is in the language or not, if it's in an infinite loop. Maybe we've waited a year and it still hasn't halted. We could say, well, it might not ever find the right thing, and then we could shut it off, but maybe on the very next try, it would have found the right path and halted. But anyway, now we have a deterministic machine that simulates this non-deterministic machine. You might wonder how we generate mom's advice. In this case, we just start incrementing or counting. And counting is something that we can do with a finite automata pretty easily, and just maybe even a binary counter or an odometer. And we'll just keep increasing and increasing our numbers until infinity. So no matter what, we'll search every single path in our machine. Now, the full point of this lecture is that there's lots of things that we can try to do to make a Turing machine more powerful. And we actually have found some things that have made it maybe more efficient, easier to write down on a piece of paper, or so that it finds the halts sooner, or something like that. But as of today, we've never found a machine or been able to kind of think up of a machine that is able to define more languages than a Turing machine. So in other words, the Turing machine is our ultimate computing machine. If there's a problem that can be solved, then a Turing machine a by anything, then a Turing machine can solve that problem as well. So we're going to talk more about that in the future. But now we're going to try to explore the limits of our Turing machine. What kind of problems can we solve with Turing machines? And more importantly, are there any problems we cannot solve with a Turing machine?